Hi everyone, Brandon here with GD&TBasics.com on the video question line. Today's topic is vendor capabilities and/or limitations with manufacturing or inspection. The question that we have today comes from Jamie, and here's his question. My question is probably more clear in my mind's eye than I am able to express in written form, so please be tolerant of my attempt to translate into a question. So he says, this is what my mind sees. A situation which, as best as the design permits, all datum references are established correctly and all necessary control frame and tolerances are defined correctly for optimal fabrication and inspection of the intended design. The hypothetical scenario that he put in here, the geometric nature of the component is such. The application of the principles of GD&T conflict with the capable manufacturing processes and/or available methods of inspection from one vendor to another. So here's his ultimate question. Is my hypothetical scenario realistic enough for consideration or concern? If yes, how do alternate vendors adapt to a defined design intent that may be regarded towards a specific manufacturing approach or intended method of inspection, for example, special tool and die fixturing? So Jamie, we felt here at GD&T Basics that this question was brilliant, and it affects, I think, most everybody out in the manufacturing world. So we wanted to respond with a video response so that everybody would get a chance to see this, everybody with any interest, and see the question for one, and then the response to this, and kind of work through this. So let me see if I can answer this without disappointing you too much. So here it goes. If the GD&T is applied correctly to the drawing, and what I mean by that is that the DRF has been established, the datum reference frame, and matches the function and the feature control frames are applied with the correct geometric tolerance and back to said DRF, it most likely will never be optimal for machining, but should be able to be inspected. So if you look at this drawing that I have up here on the screen, the datum reference frame, which by the way, this is our clevis bracket. We have a full 5-part series webinar on this in the video and webinar content in your dashboard. So if you want to go back and take a look at how we worked from the manufactured drawing or the mechanical drawing from stage 1, which would be coordinate dimensioning, all the way through into the fundamental application of GD&T, along with the inspection plans, and then the advanced with the inspection plans. That's all available to all of our students. So please take a look at that. I'm not going to discuss really any of that much more through this, but please, you have that at your advantage. Go back and take a look at it. So if we look at this print, this is the one that we consider to be the advanced. And by advanced, what we really mean is designed for manufacturing. So we are taking, we do look at these parts, and we're always considering manufacturing. If there's anything that we can do to make manufacturing more simple, then we're going to do it. Manufacturing doesn't always necessarily mean the machining part of it. It's the broad scope of manufacturing. Maybe we want to functionally gauge this out on the floor in process. So we may change up the drawing. We want to keep the datums, like we said, that simulate the actual functionality of the component. I've included this little assembly image over here on the left side, just to show you that this clevis bracket, for anybody that has never seen this before, is mounted to the back of this air cylinder. It's flush up against the face of this back air cylinder plate. And then there are 4 bolts that are holding it to that. So just a quick glance at this drawing, we are relating back to how this assembles. If we look at datum A here, datum feature A, it's this back surface. Well, like I just said, it mounts on this surface back here. If you think of how you would actually assemble this part, that you're going to take this clevis bracket and rest it upon that face on this black component. So you're going to rest it on that face. That's the first thing that happens in the assembly. So on our drawing, it's the primary datum. The The second thing that's going to happen with this whenever we assemble it is we're going to put in the 4 bolts. So we're not doing alignment around the exterior of this. We're placing the 4 bolts in there, and that's going to not only locate it, but it's going to stop the rotation. So it's going to orient this part to the assembly as well. So that's why datum feature B is up here on the 4 bolt holes. And then when we go back and look at all of the datum reference frames that are used in the feature control frames, like I said, this position right here, well, we're telling quality that what matters for this feature is 3.5 inches wide with a tolerance plus nothing minus 20 thousandths. It has a position tolerance of 40 thousandths, but in reference back to A and B. So we want quality to lock it down on A and B. That does not mean that quality can first go in and lock it down on the 4 holes and then on the bottom surface. The DRF, or the datum reference frame, is explicit. It tells quality you must first lock it down on A. This surface needs to be secured first, and then secure the 4 holes. Which one of them first doesn't matter. We have a pattern of 4, so it's all 4. So that in reality, you will be engaging on one first, then the second, then the third, then the fourth. That's the way the bolts are going to go in. But what it means on the drawing is that all 4 of them as a pattern, as a whole, or as an entirety. So we want it locked down A first and then B. That mimics the function of it. So we want to inspect it so that it mimics the function. So that's what we put on our drawing. This takes a lot of the ambiguity out of this, because anybody, if we sent this out to 3 different vendors and they're looking at this drawing, there will only be one interpretation to it. These feature control frames with the datum reference frames within them, it's put in there so that every single person interpreting the print will interpret the same way. And they understand that it will be locked down on first on A and then on B. And even going over to this composite tolerance over here, the first frame here is to A and B, right? So the rules of composite, the first frame is just like any other position. So it is being oriented to A and then located from B for these 2 holes. So quality has to lock it down in that same fashion. So quality doesn't need to ask the question of how does this go into the assembly? What's the most critical part of this? How does it function? We're doing that with GD&T. We're showing all of that on the drawing with GD&T. So as long as this is done accurately, the person, whoever's applying this to the drawing, the datums have been established according to the function, and all these feature control frames with these features are relating back to the way that they will individually function within the assembly, then we've got a good drawing here. Now, like I said, this most likely will not be optimal for machining. We understand that, and machinists understand that as well, as long as they understand the GD&T that's on the drawing. But in the order of the machining process, and we talk about this a lot in training, is even though this is the primary, machining is not going to come in here and machine this first. That's not going to happen, so that they can get this all accurate or this accurate. They're not going to do A first. They're going to look at this and take an attack on how to get all of the material out of there, rough it all out. It's going to move. The material will definitely move as it gets machined. It's going to stress relieve. So as they go through and machine this, then eventually they will come back and get these datums. So they may rough out, all of this material around through here. They may get all of that out and rough it all out, leave a little bit of material for finish. They may choose to come back in after they rough it out and then machine this back surface, understanding that now it's going to be stable. But that could also be the very last surface that they machine. They could fixture this in a way afterwards that they come back in. They may do the counter bores over here from this back surface, but they may finish all of this. They may finish the counter bores and then flip it over and then come back in, skin this face, take the rest of the material off here and put in the through holes. After all, those are the primary and secondary datums. But We don't want to try to tell them how to do it. We only need to put on the print what's functionally required. And that relates back to that assembly. What's required from the assembly? How will it actually function? What do we need to be inspected, but also accurately located or oriented, whatever the requirements are, in order for it to function properly? And that's what we tell quality with this drawing to do, is come back and inspect it this way. Manufacturing, you take this and understand what your limitations are, and understand that this is what we need when it's all said and done. But in no way are we trying to dictate the manufacturing process of it. So that's completely up to the manufacturing department. Okay, so this is a concept, doing drawings like this, it's a concept that took me a while to accept. So I'm a machinist and an engineer. When I started my career, I would make these mechanical drawings. And the drawings, this one over here on the left, I'm calling this one a mechanical drawing. They are truly any of these drawings we make are mechanical drawings, but going back to a coordinate dimension print, this is the way that I learned how to make prints. Back in the beginning of my career, we didn't use a whole lot of GD&T. One company would, another company wouldn't. It's still a lot like that today, but definitely back then it wasn't as prevalent as it is now. But on this drawing on the left-hand side, this is what we would make. And a lot of times we would have notes, like let's say on this through hole here, we would put a note on there if it was highly accurate. When we may put the word ream in there. We're not supposed to do that anymore, according to Y14.5, ASME Y14.5. We're not supposed to put on there what the manufacturing process is. In reality today, if we did have ream on here, more than likely the machinist is probably going to use an end mill on CNC and circular interpolate these holes, even if it is a very, very tight tolerance, because they have more control over that end mill than they do a reamer. A reamer, depending on how much runout you have in it, when you go into a hole, you get what you get. There are machinists have little tricks to influence those reamers and get them to cut slightly oversized, but with an end mill, we can do anything. We can put cutter comp in there and we can run it, we can rough it out with that end mill 10,000 smaller and then come back in and finish it with the exact same one using a rough finisher. So on the drawing, we're not supposed to dictate what those manufacturing processes are. Now, this doesn't mean that the engineer is not to consider the method of manufacture or the process of inspection. We're always supposed to be mindful of that. What's the point of making a perfect drawing with GD&T that nobody can make or inspect? So we don't, and I've worked with engineers that do this, that their plan of attack on a drawing is go in there and just load it up with GD&T and a lot of complex GD&T, and it's not the point of this. We want to make sure that we're not sending anything out to the floor that can't be made, or something that would have to go to a CMM to be inspected, but our quality department doesn't even have a CMM. If we're a company that is constantly contracting CMM work out, okay. But if we're sending it to our inspection department and forcing them to inspect it, what are they supposed to do if they don't have this CMM? So we are supposed to consider that. If we can't inspect it, let's take a different approach to it. Let's do something else. Maybe we can change some of these inspections to simple caliper checks, or maybe we can change our inspection plan so that we're only using a height gauge or something like that to verify a few points of profile tolerance maybe. But we do have to keep that in mind. So consider this though for manufacturing. And this is really a question for you, Jamie. Would it be the GD&T on the print that could make something impossible to make, or simply the tolerancing? So in GD&T, we're supposed to make tolerances looser, not tighter. GD&T is not supposed to be complex. It's supposed to be simple to understand. Yeah, we know you have to have training. Somebody's got to tell you what it is, what the rules of it are. But if you go through our course, and hopefully all of you have found this that have completed certain segments, or maybe you're entirely done with our course, we make it very simple to understand. And we don't try to dive too deep down into the standard. We're trying to show you the simple rules about each one of these. And everybody needs to understand these inside of your department or inside of your facility, from engineering through manufacturing down into quality. So we don't want to make it any tighter. And if you look at this drawing here, hopefully it's not hard to see, but just looking at the two bores here, the original drawing had on here in line within 1/1000th. And this is in inches, so it's in line within 1/1000th of an inch. But look at the location of them. So look at the tolerance on this one is 3.5 thousandths plus or minus, coming from the bottom of the part, which we did say, the bottom of the part is important, right? Over here, it's primary datum. But now look, we're coming off this bottom rail down here, and we have plus or minus 3.5 thousandths here from the bottom up. That does not relate to function whatsoever. If we come back over here, we have a position. It's composite position, but it's back to A and B. Now that is to the bottom and to these 4 holes. So that's directly relating back to the function of the part. But we also opened up the tolerances substantially. We've got a 20 thousandths for location here back to the datum reference frame. Over here, like I said, from the bottom, we're plus or minus 3.5 up, and from the bottom rail here, we're up 3.5 thousandths as well. Well, converting this over to GD&T, we're still holding, down on the lower frame here back to A. This is composite, so it's holding the 2 holes together within 1/1000th. So that is holding them in line within 1/1000th. So thousandths coaxial to each other. But we've put on here, we don't have to be so tight back to the datum reference frame. So we're within 20 thousandths back to the datum reference frame. Well, that's something that we wouldn't have been able to do over here. We can't come back to this global datum reference frame and put these dimensions on here. It doesn't happen that way with a coordinate dimension print. We pick, normally we use baseline, so we've said, well, this is where we're going to pull all of these dimensions from, so that we're 9/16 up, 4-inch square pattern here. We're coming from that bottom frame, because with this type of dimension, now we could have come off of right here, but then over here on the side, we would need to have dimensions related back here, just using this section view over here as an example, back to the center. We could have done that, but we still would not have cylindrical tolerance zones like we do with GD&T. It would still be a much tighter control. So with this GD&T, we're able to loosen all these tolerances and show the actual functional requirements, the design intent on here, the functional requirements on this. And like I said before, if it's applied correctly, the tolerances really should be looser, because the engineer is supposed to do his or her job and perform calculations to see where the tolerances can be loosened or tightened if they needed to be. Sometimes we go convert drawings from coordinate dimensioning over to GD&T and realize that there were certain things that the engineer that originally did this drawing didn't consider. What could really happen with with this type of drawing over here, when we do have these square tolerance zones, what can really happen? So sometimes they do get a little bit tighter, but again, if they get tighter, it's because it's functionally required. We're not supposed to be tightening up in any way. So when we do this conversion over here, we're using GD&T now. On this conversion, and you were referring to the capable manufacturing processes, the question really is, did we make the tolerances any tighter? So like I said, we're not supposed to make them tighter. If we had to, then we will, but we're not supposed to do that. And when we convert it over to GD&T, we are supposed to be loosening tolerances if at all possible. So the application of GD&T to this print is not making anything any tighter. As far as your manufacturing processes go, it shouldn't affect those in any way. GD&T should never affect that part of it. Because after all, what we had over here on this coordinate dimension print, the expectations are still the same over here. The only difference is we are fully defining with GD&T how this thing will function and how we need everything related back in order to function. And like this drawing shows over here on the right, this is directly at the true function of this component. A being the bottom, and then the bolt pattern actually attaching it to that air cylinder. that shows that exactly. And the datum reference frames are really what come back and call that up and show that that's truly what it is. And all of these have an A and B reference. So it's back to that bottom plane and then the bolt pattern. If we come back over here and look at the coordinate dimension print, most of them are coming from this bottom over here, but now look over here, we're coming from the side. So these are all coming from this one side over here. Again, like I said, the outside serves zero purpose, and that's what this drawing over here is showing. It's doing the exact opposite. What it's doing is it's taking the outside profile of this part, or the perimeter, and now locating and orienting it back to the ABDRF, or the bottom face, and then the bolt pattern. So it's bringing it and relating it back to that pattern instead of from a side that is meaningless. So we're able to do that with GD&T and be more clear and specific about it. But like I said, also we are supposed to be opening up those tolerances if we can do it. Do a little bit of homework, see where you can go back in and open up tolerances. Like I said, this should not affect the manufacturing processes at all. If anything, it should make it easier with using GD&T, provided that the machinist know how to interpret this GD&T. This print over here, the GD&T print, in no way states that whenever they put this part in there to put it in the counter bores that they have to secure this and then secure those 4 holes. Like I said a while ago, it's not going to be that way at all. They could just simply put this up against the back jaw of their vise and then having a stop over here to the left side and sliding the part up there. But they have to know, if they did machine that outside profile first and they're going to do this, they have to know where they're at and where they need to be. And they can take this, it's called a work fixture offset, but they can take this and shift this if they need to. This would be the one for X. This one over here, which would be this front face, this would be the one for Y. They can shift those any way they need to, comp those, if you will, any way they need to in order to get this part to sit where it needs to, in order to put in the through holes if they wanted to at this point. It's sitting on A, so they could put in the through holes and the counter bores together. But like I said, they get to choose how to do this any way they want. But the intent is never to tighten up those tolerances. It's to loosen them. And again, we're not telling manufacturing how to do this at all. So the comparison between these two drawings, either one of them in a perfect world, either one of them should be able to go through the machining department and get the same result. But definitely when it gets to quality, this is going to be very specific to quality on how to inspect it, where this one's not. So, and that's all of us that have been in manufacturing for a long time. It's you have to take a lot of gambles when you're dealing with coordinate dimension prints like this on how to set it up and how to inspect it, and what's really necessary for the function of the part. So you're going back working with engineering, and a lot of times quality will try to, if there's no better way, will try to mimic how it was machined, and that's really all. It's a bad idea. Having this over here is very specific. It's very clear. Lock it down on A first, then on B, then take your inspections. There's no other interpretation to that. So no questioning. We don't need to go back and ask engineering, how are we going to do this? So now on the flip side of this, the manufacturer may not know GD&T. So if you are subcontracting this out, and your original question was about vendors and capabilities of those vendors, and excuse me, especially when you're dealing with multiple vendors, you may have a vendor that has a CMM and will give you good results every single time. You may have another one that doesn't have a CMM, and they're doing a lot of this with height gauges and pins and whatnot. And I'm referring to the GD&T print right now. If they don't understand the GD&T, it can cause prices to go up. I've dealt with this personally. So it can cause your prices to go up. I've also had vendors just give no quotes. They see the GD&T on there, they think that it's too complex, so they'll no quote it. And then I've also had vendors that don't know the GD&T on the print. They don't understand it. They don't want to take the time to ask about it. So they'll just do the best they can, which is really, they're kind of taking this approach to it. They're just going to come off of a surface because they don't understand the datums and give you the best thing they can give you. So you may wind up with bad parts, and that's another result of this. So when we're working with companies like doing a rollout, so we help companies do a rollout of GD&T, and part of that whole process is understanding the whole chain and who's going to be affected by this whenever you do decide to roll it out. Who are the stakeholders who need to be involved with this rollout process, and a lot of times it's vendors. And if you have vendors that don't understand GD&T, well, you may make the decision to put them under your wing and kind of help them interpolate these drawings and understand it. And you may go the alternate route and say, well, if you don't understand GD&T, we're not going to work with you anymore. That's definitely not always the best process. I've worked with a lot of great vendors that produce wonderful parts. Some of them I still work with. They don't know GD&T. Some of them are just stubborn and don't want to learn it. And in the rollout process, you have to kind of understand or write out, how are you going to deal with these particular vendors? You could have vendors that you've been working with for 20 years, 40 years, 50 years, and you don't want to lose them as vendors when you switch to GD&T. So there has to be some communication and involvement there early on with them. See if they are willing to get training on GD&T, or maybe what you're sending to them is so small that you can either choose, if you know that the part's going to go to them, maybe you never put GD&T on it, or you put GD&T on it. Like I said, you work with them specifically on how to inspect the actual part, because they don't need to know the manufacturing part of it. They need to know their limitations, and that's really going to be, when it comes down to inspection, what's really critical and what kind of approach should they take at inspecting those parts. So, and then, on the side of inspection, and really deep down, we're creating an inspection document with this drawing, right? It's supposed to convey our design intent. It's supposed to have the functional requirements of the component back to its assembly environment. But truly, at the end of the line, this is going to be an inspection document, and this is telling quality exactly how to inspect it. And the standard states that we should apply all the necessary geometric tolerances for guaranteeing that function. And like I said earlier, that's great, but what if you apply a profile tolerance and you don't have a CMM to measure it? Well, in the standard, it states that with profile, within reason, you can use calipers for checking or height gauges. And when it gets to real complex geometry, there are limitations there with traditional inspection equipment. I have taken parts that have complex profile on it and put them on a Bridgeport with a digital readout and use that to find my points. But what I wound up having to do is go back into the CAD model, get these points, which are basic dimensions, get these points and basically put a table on the inspection plan and say, okay, well, if you can set it up with this being X and this being Y, secured down, in Z, hopefully representing the datum reference frame, then we can take an edge finder or a probe and we can run out to these absolute points and come in and touch off, and we know a range of where we have to be on that forward profile. So we will work with our customers, our students. We will teach, I always call them cheat methods. They're not really cheat methods. We're still trying to adhere to the standard. We're still trying to adhere to the correct inspection of this complex profile. But we're trying to find an easy way to do it, something that doesn't require the CMM. So we help customers with that. And again, we're not breaking the rules of the standard. We're just trying to find a workaround that's realistic and doesn't force somebody to either remove profile from their print or to go out and buy a $50,000, $100,000 CMM in order to inspect a single part. That makes no sense, and that's definitely not what we're about. We're not trying to get people to do that kind of stuff. We want to find a method for inspection that gives them good results and repeatable results, right? So if we can inspect one part one way and validate it and know that it functions, checking those points, well, now we have a process that's repeatable. and we'll show them how to make it repeatable and consistent. So on this, just trying to conclude this here, Jamie, GD&T is used to make sure that the part functions properly. That's first and foremost. And like I said, coordinate dimensions don't convey that. Even just on simple shafts, stuff like that, it's not conveyed. When you look at two cylinders that from a right side view that are appear to be coaxial, well, how coaxial do they have to be? On a coordinate dimension print, there's nothing there to tell you that. Doesn't mean that you can't have notes hidden away in maybe even in the title block. You can have it in the title block. You could have maybe supporting documents that say anything that's shown to be coaxial is coaxial within this amount. What that truly relates back to, and you have to go back, is it a circular tolerance zone? Is it a square tolerance zone? How are you going to handle it? But simply put, you're wording out position tolerance from GD&T. So the coordinate dimension print itself, it doesn't convey all of that. We want it conveyed with GD&T. We want it to have datums. We want it to be clear, one universal interpretation of the print. That's the whole point of GD&T. And like I said earlier, we want to be able to loosen tolerances where we can, because we're just looking at the function of the part. And all of those things that don't matter, just like we show in all of our webinar series, when we have surface features that don't matter. Now, I say that loosely. Everything matters on there, right? It wouldn't be there if it wasn't needed in some way. But we have some parts that require tighter tolerancing and other features, and then other features that we could stand to open up the tolerance. And we'll do that. We'll go back and open it up. We show that in our webinar series. We may give a profile of something all around 30,000, 60,000, 80,000. If it really can float that much, if these surface features can go out that far, then put it on the print. Engineers definitely get scared on a coordinate dimension print on how do you actually do that and not have something that's just terrible looking. Well, with GD&T, we can do it because we're zeroing in on here's the datums, and then here are all the features, whether it's a surface feature or a feature of size, and then we're using geometric controls, and not always, but using geometric controls then to relate that back to the datum reference frame if that's what's functionally required. Now, we still use coordinate dimension tolerancing on our drawings because sometimes it just makes better sense. We don't have to slap a profile tolerance on there if we don't feel it necessary. But if we know that the part's already going to be locked down in a CMM for these inspections, then we'll include these as well. We'll go in there and add profile in there. Because remember the rule, if it doesn't relate back to the datum reference frame through geometric controls, it cannot be inspected using that datum reference frame. It would be just simple size checks or whatever. So we'll put it on there if we can, if it makes sense. But if it doesn't make sense, we're not going to do it. So just looking through these on the design, is the tolerance necessary for function? So like I said, loosen it up if you can loosen it up. Try not to ever tighten it up unless that's what truly was required in the first place. So like I said, that's not going to the next one, is the part being created properly, knowing the functional intent? It's not going to affect the manufacturing of that part, or shouldn't. They may choose to use functional gauging, which our GD&T print's going to help with that. Now with GD&T, features at their MMC, now we can do functional gauges and do real quick inspections out on the floor and not bother quality with that. And then down on the measurement inspection side, is the part being measured in a way to mimic the functional operation? That relates back to those datum reference frames, and is quality following the rules for those datum reference frames that are in the feature control frames that are telling them exactly how to inspect that part. Okay, so Jamie, that was very, very long. I hope that answered the question. And we love questions like this, by the way. These are great. It's not relating specifically to any kind of GD&T symbols, but this is a big part of GD&T, and we know that this is a struggle that a lot of companies have, especially if you haven't converted over to GD&T and you're considering it for whatever your needs are. Whether your customer's driving it or it's an internal drive to just have a better better drawings, a better understanding or interpretation of the drawings, whatever the reason is. So if you have more questions like that, please send it in to us, www.gdntbasics.com. You can go there for our website, questions, just simply questions@gdntbasics.com. We would love to hear from you. We hope that you enjoyed this one here and got some useful information out of it. And we hope to see you again. Thanks, everyone.